and the problem or challenges we aim or want to or can solve with our vacuum insulation energy technologies. As usual, we always start with this. Although we could talk about the semantics of it for hours and hours, to put it simply, climate change is scientifically linked to carbon emissions. Because of that, we now hear so many ideological terms such as go green, net zero, energy, net zero minus, zero emissions, sustainability, renewable energy, clean energy, low carbon, sustainable development goals, and so on. And mostly we end up with a tick box exercise, a checklist of jargon filled ambitions ticked off one by one, while the real problems quietly continue to grow. It all sounds promising on paper, but in practice, very little changes unless we act where it truly matters. But the main purpose behind all of this is to find a genuine balance between reducing carbon emissions and meeting the rising global energy demand. Why? Because we are constantly building and expanding, and even population growth need to be supported. In fact, phrases like net zero have become the punchline in almost every research paper in the energy and built environment sector. Ironically, some of these papers end up increasing carbon emissions themselves. By running endless simulations that have little or no connection to what's actually happening in the real world, to achieve true balance, we must either generate more energy through renewable or non-renewable power plants, or we reduce energy loss. That's where insulation becomes crucial. And among all types, vacuum insulation performs the best, which we are going to examine throughout this keynote speech. A simple analogy is, imagine a bucket with holes. If we keep pouring water into it, we need more and more water just to keep it full. But if we reduce the holes, we obviously reduce the water loss. In this analogy, the water is energy in kilowatt hours. Approximate percentage of buildings that are not insulated. For example, my research indicates in the United Kingdom there are 20% buildings which are not insulated, Saudi Arabia 70%, UAE 50%, Italy 50%, Kuwait 20%, Qatar 50 to 60%, Germany 42%, Bahrain 60 to 70%, and Oman 90%. Now, higher the percentage, greater the cooling energy loss or heating energy loss depending on the climate. Approximate percentage of buildings that are partially or fully insulated. Again, my research indicates that in the United Kingdom, there are about 40% of the buildings which are either partially insulated or fully insulated. Saudi Arabia, 5 to 10%. UAE 50%, Italy 20 to 30%, Kuwait 50%, Qatar 10%, Germany 28%, Bahrain 10%, and Oman 10%. In this, lower the percentage, greater the cooling energy loss or heating energy loss. Well, of course, energy prices in the Middle East are much lower due to reduced tariffs, and the cost-benefit ratio may suggest otherwise. So aside from national initiatives on energy efficiency, why should we insulate if it only increases construction cost? A very important question. So the realistic reasons are, number one, reducing cooling energy loss lowers the air conditioning load, allowing it to turn off for short periods, which helps extend its lifespan and reduces expensive repair cost. Number two reason, from a nationwide perspective, reducing cooling energy loss cuts energy demand and conserves fossil fuels. Even a 10% saving could match the output of a renewable energy power plant. Number three reason, energy prices keep rising, yet buildings last for centuries, not for decades, not for 50 years, but for centuries. So the decision made today will impact generations. Look at what happened in the United Kingdom, where many homes remain uninsulated. Energy costs are among the highest globally, leading to the harsh choice between heating or eating. Number fourth reason is humanity naturally progresses forward from one innovation that was good in the past to another that is better for the present and the future until something even better comes along. At the moment, vacuum insulation is the present and the future. Now, imagine a residential building with no insulation in a hot climate, say 40 degrees Celsius. At the moment, in the month of June 2025, as I'm recording this video, the temperature in Riyadh is about 44 or 45 degrees Celsius. But let's imagine that when the air conditioning is on, it feels comfortable. There is nothing to worry about. But what happens when the air conditioning is off for a few hours during the day? That same space can eventually turn into a virtual oven. If the same building, for example, or if the building is made of beautiful shiny glasses, under the same conditions, it could easily turn into a virtual cooker. On the off chance you are a real estate developer or a building construction decision maker, here is a question for you. What is your unique selling point compared to others? Most new or old builds are marketed with usual talk luxury facilities, glossy brochures, and beautiful advertisements. But when a buyer asks a simple question, how is the building made? What materials are actually used in the apartment that I anticipate to buy, for example? The answer is often vague, with no clear specifics, a hollow promise rather than a solid response. But the fact remains, it's always the buyer, the customer, who ends up paying the energy bills. People who buy today will one day retire, and when regular income is no longer there, energy costs will still be part of their lives. It is something they will have to factor in during their pension years. That's why a building must be energy efficient and well insulated. Well, we use concrete and bricks in building construction, and of course, we must, because the buildings we constructed today are meant to last for hundreds of years. The decisions we make now will directly impact the lives of future generations living in those buildings. Take the United Kingdom as an example. We have thousands of heritage and older buildings built decades or even centuries ago. Many of them are now classed as hard to treat or hard to retrofit, and they consume far more heating energy just to keep the inside warm. With the UK now having some of the highest energy prices in the world, we are seeing the widely known phrase come to life, which is heating or eating, a harsh reality during the ongoing cost of living crisis. The concrete wall, let's begin with the thermal conductivity, which is a measure of how easily heat can pass through a material. If a material has a very high thermal conductivity number, like the concrete wall that has 1630 milliwatt per meter per Kelvin, It lets heat move through it quickly. U value, or thermal transmittance, is a measure of how much heat passes through a building element, like a wall, window, or roof. In this case, concrete wall has a higher U value of 3.4 watt per meter square per Kelvin. Lower the thermal conductivity or U value, better the insulation, lower the losses. This could mean that most of the buildings that we have in the United Kingdom are either solid brick wall, which has a thermal conductivity of approximately 840 milliwatt per meter per Kelvin and a U value of 2.3. It is slightly better than a concrete wall, but still far too much heat passes through it. We are going to examine all of it when we apply vacuum insulation panel. This cavity wall, which is quite normal nowadays for new building constructions, that has a thermal conductivity of approximately 380 and a U value of 1.5 watt per meter square per Kelvin. It is better than both solid brick and concrete walls, but there is still considerable energy loss, which we can and should be reducing. Later, we will see how these numbers can be reduced with vacuum insulation to levels that truly show what energy efficiency really means, or when we minimize the leakage of cooling or heating energy loss with it. So what are the limitations of the conventional insulation materials? Which are they and why? We are going to begin with our famous insulation. I hope we can settle this once and for all. EPS, expanded polystyrene, was invented in 1949 in Germany and has been widely used for insulation and packaging ever since. It's a type of thermoplastic polymer like this one, right? Like EPS and XPS, however, it is flammable and can catch fire easily, with a fire rating of class E according to the BSEN 135011 standard. Even when treated with fire retardants, its fire resistance remain limited. It has lower thermal performance compared to other insulation material. Furthermore, EPS degrades with exposure to atmospheric humidity and temperature, making it less durable over time. Additionally, it can attract insects like ants and spiders, and fungus or mold can develop on it. In expensive buildings, using EPS means future refurbishment costs must be considered, as it will likely need replacing after some years. It also needs more thickness to provide the required insulation, which takes up valuable space. Of course, EPS is cheap to buy and easy to cut on site, but its long-term performance and risk must not be overlooked. PIR insulation board is a type of thermostat polymer, a form of plastic. It offers better thermal resistance than EPS, but still needs to be fairly thick to achieve improved performance. PIR has a Class B fire rating according to the BSEN 135011 standard, which means it provides better fire resistance than EPS. However, it is still flammable and can catch fire under extreme conditions. PIR also tends to attract dust, and although it degrades more slowly than EPS when exposed to humidity or changing temperature, it still shows signs of wear over time. PIR is more expensive than EPS, and its bulkier size and heavier weight mean transportation costs must also be considered and are typically higher. That makes it a less cost-effective option in many cases. It can be cut on site during construction, which is useful, but when you weigh up the higher price, transportation challenges, and the fact that it is still combustible and prone to long-term degradation, PIR becomes a less appealing choice for many building projects, despite its modest improvement in fire and thermal performance. Rock mineral wool is often praised for its higher fire resistance. It can achieve a Class A1 fire rating under BSEN 135011 standard, meaning it is non-combustible. However, beyond fire performance, there are important limitations to consider. First, it needs to be thicker in its size that require more space, and if we were to look at it microstructurally, mineral wool has an open fibrous structure that easily traps dust, moisture vapor, and airborne water particles. Over time, this creates an environment where insects can nest and fungus or mold can develop, especially in humid or poorly ventilated spaces. This may lead to unpleasant smells, reduced air quality, and degradation of insulation performance due to trapped moisture in it. While mineral wool performs well in fire resistance scenarios, its vulnerability to biological contamination and moisture related deterioration makes it less ideal for long term enclosed applications, particularly where vapor control is critical. Similarly, glass mineral wool is widely used in building construction and it is known for its non-combustibility, often achieving a Class A1 fire rating under BSE and ISO 135011 standard. Similar to rock wool, again, it needs to be thicker in its size that require more space. However, when we examine its practical and microstructural limitations, several concerns arise that are its open, fibrous structure makes it highly absorbent to moisture vapor, or even over time it can trap dust, dirt, insects, and airborne pollutants. However, moisture vapor is one of the important point that needs to be considered when it comes to the insulation. However, the lifeline is lower. In humid conditions or areas with poor ventilation, this can lead to fungus and mold growth, which may result in an unpleasant smell and compromise indoor air quality. The accumulated moisture can also increase thermal conductivity of the insulation over time, although it performs well in terms of fire resistance and initial cost. Glass wool is sensitive to environmental conditions. Without proper vapor barriers and maintenance, it may degrade, lose effectiveness, and become a source of biological contamination, making it less suitable for long-term sealed or high humid applications. This brings us to a very important discussion: what is vacuum? When we reduce the atmospheric air pressure or remove air molecules from 101.325 kilopascal down to between 1 pascal and 10 pascal, we create a moderate vacuum. This is the level we apply in our vacuum insulation energy technologies. What does the vacuum do? Well, it reduces heat transfer, that is vacuum insulation, meaning it saves energy. It reduces noise, that is sound insulation, meaning we could have a good night's sleep in a city center or in a busy large city centers. And it limits fire propagation, that is fire resistance. That means it minimizes the damage caused by unusual fires that can occur in any building. This brings us into the age of vacuum.